In the second half of 4.1, we're going to be talking about finding relative extrema. Now that phrase, relative extrema or relative extrema, has a meaning. We'll get into that in a minute. Using the first derivative test. So this is what we're going to look at. Now relative extrema, this means extreme, it's a plural, okay, of extreme. So extremum is singular, extrema is plural, relatively speaking. So it's a relative extreme value, relative max, or relative min, depending upon the question. Okay, so how do we use the first derivative to determine the relative extrema? The procedure is very simple. So the process or the procedure of the first derivative test. So what you do is first, step 1, find all critical points of f of x. And brief recall from the previous video, to do this you see where f prime of x is 0 or where f prime of x is undefined. Let's say C is a critical point. Let x equals C be a critical point. If f prime of x changes from a negative to a positive value on either side of C, then there is a relative blank at C. We're going to fill in the blank in just a minute. You need to visualize this. So if C is your critical point, I'm just going to draw a number line here. C is right there. And what the statement is saying is if f prime changes from being minus to plus, we always go from left to right on both sides of C, that means the function f was decreasing to the left, and if f prime, I should have a prime there, if f prime is positive, then what is f doing? F is increasing. So this means it's going down, 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 and then up, up, up. So right there is a valley point, meaning you have a relative minimum. Okay, so there's nothing really very new in this section. It's just taking what we saw in the last section and adding a little bit more to it by just doing the number line again. So this is, we can call this part A. In this procedure, part B says if f prime of x changes from positive to negative on either side of C, going from left to right, then the opposite happens. There is a relative maximum at C. In one last case, part C, is if f prime of x does not change sign, meaning it's negative and then negative again, or positive and positive again, then there is no relative extrema, and that happens sometimes at C. An example for the last case is if you have f of x equals x to the third power. Let's say it's x cubed plus 5, and you find f prime of x, you get 3x squared. To find the critical number, we set this to equal 0, and the only solution is x equals 0, because you divide by 3, you get x squared is 0, take square roots, x is 0. So this is your critical point. If you draw a number line, and there's 0, you have negative 1 and 1 as sample points, plug them into f prime. And you'll notice that since this is a square, negative 1 squared is positive, so it's 3 times negative 1 squared, it's a positive value, function is increasing, plug in 1, it's 3 times 1 squared, which is 3, positive still, so it's increasing and increasing. If you were to graph this on your calculator, you'd get a graph that looks kind of like this. So it's always increasing as you go from left to right. So that's an example of the third case. Most of the examples in your homework will be more like the first two, where you actually have a max or min. Alright, in the next worksheet that I have along with this video, we're going to do only a portion of the first problem, and then we'll take a break and do a different lecture for the rest of this topic. I'm doing 4.2 as well in this video. So in the worksheet here, we have f of x is 2x cubed plus 3x squared minus 12x. To find the critical numbers, we need the first derivative, f prime of x, which is 6x squared plus 6x minus 12. To solve for critical numbers, we need to set this to equal 0. So this is a quadratic. We need to refresh our memory on how to solve this. Let's take out a 6, x squared plus x minus 2. Can divide the 6 and get rid of it. 0 divided by 6 is still 0. And this factors as x plus 2 times x minus 1. Set each of these to be 0. We get negative 2 and 1 from each of the factors. These are our critical numbers, our critical points. Okay, so now the intervals where it's increasing and decreasing, we'll just draw a number line. Since we have two critical points, we'll have to divide the number line into 3 regions. Okay, so let's say I pick a sample point from here, and here. You can pick whatever you want from each of the regions. But remember that all of these get plugged in into the first derivative, f prime at negative 3. We need f prime at 0 and f prime at 2. Now you could plug in negative 3 into that, or you can plug it into the factored form, because we really had a 6 here, and that the change of the sign doesn't happen there. So if I plug negative 3 here, it's easier than plugging it over there. It doesn't matter if you're using a calculator, either of those would be fine. Negative 3 plus 2 is negative. Negative 3 minus 1 is negative, so this is positive. If f prime is positive, f is increasing. Let's plug in 0. 0 is pretty easy to plug in here. You get 0, 0, negative 12. So it's negative, which means f is decreasing. Plug in 2. I'm going to put it in here. 2 plus 2 is positive. 2 minus 1 is positive. Positive. So f is increasing. The way we write our answer, though, is we say f is increasing from left to right on the interval on negative infinity to negative 2 union 1 to infinity. F is decreasing on this interval from negative 2 to 1. All this. On the first derivative test, I didn't give you a lot of space here because you don't need a lot of space. You just use the same number line to come up with the answer here. So you use your results from part B and the first derivative test to determine the relative max and min. So up here it's going up and back down, changing from positive, f prime positive, f prime negative. That's a peak. So you'd say a max at negative 2 comma, I'm going to leave a blank, and then down here it's decreasing and then increasing, so it's a relative minimum at this point 1 comma something. Now these max and min points are points on the graph, so we actually need the x value and the y value. To find the y value, we're going to use the function f, so it's f at negative 2, f at 1, and f is up here, so we need to plug it in there. So I'm going to do that here, negative 2 comma, if I plug in negative 2 there, it's 2 times negative 8 plus 3 times 4, and feel free to use your calculator here. Negative 16 plus 12 plus 24, it's 36 minus 16, I'm getting 20. Plug in 1 there, that's easy. 2 plus 3 minus 12 is negative 7. So we're going to pause with the worksheet here and return to our lecture, because we're going to take a look at what 4.2 is all about. Section 4.2 discusses couple topics. It talks about concavity, and it talks about the second derivative test. So to understand both these topics, we're going to need the second derivative. But before I even get into that, I want us to look at a graph again. Let's say this is time again, and this is profit again. Let's suppose the profit takes this path. Going from left to right, you'll notice that the profit is increasing. But is it increasing at the same rate? If you look here, it's increasing faster, whereas from somewhere here, which isn't a max or a min because it's always increasing, you notice that it's starting to slow down. Now in economics, this point has a name. You may remember this. When I teach in a face-to-face class, we actually play a hangman game to figure out what this word is, what that point is called in economics. It's called the point of, hope you're getting this, diminishing returns. Hope that rings a bell and jogs your memory from econ. But what's happening is that here your returns are diminishing. They're getting lesser and lesser. Let's think about this in calculus terms. Now since the function is always increasing, if I drew tangent lines here, let's pick 3 points. The tangent line slope is positive, positive, positive. But look at the lines themselves. The slope here is not as steep as it is here and here. This is steeper, harder to climb. But over here, it was steeper, but now it's not as steep. So if you're measuring how fast something is changing, we look at the derivative. So how fast means we look at the derivative. But now this is f prime. These are all slopes of the tangent line. They're all the first derivative. If we want to see how fast f prime is changing, we need the derivative of the first derivative. So we need the derivative of f prime. In other words, we need f double prime. Aha! This is why we learned second derivatives earlier in chapter 3. So what you might notice here is that this function is curving up this way, okay, and then it's curving down. So this is called concave up, and this is where it's concave down. It's curving down. And notice here that f prime is increasing, and here f prime is decreasing. So in the last section we saw if f is increasing, f prime was positive, and if f is decreasing, f prime was negative. So by using the same logic in this section, so this is from section 4.1. In this section then the logic should say is if f prime is increasing, this is f prime, is getting steeper, then its derivative, which is f double prime, should be positive, and if f prime is decreasing, then f double prime is negative. So as far as concavity goes, we say that f of x is concave upward. The graph is curving up, concave upward. We can use this symbol, it's cupping up, if the second derivative of x, this part, is positive, and f of x is concave downward, curving down, if f double prime of x is negative. One of the ways I have students remember this is to say that if you're a positive person, you smile a lot, and think of that as a smile. If you're a negative person, you frown a lot, think of that as a frown. So those two go together. So concavity is interesting. It plays a huge role in applications and economics and other parts of science as well. This point in econ, that's called the point of diminishing returns, actually is where the second derivative is 0. And in calculus it has its own name. It's called the point of not diminishing returns, but point of inflection. So x equals a is a point of inflection. We abbreviate POI, not to be confused with the Hawaiian delicacy. POI, point of inflection. X equals a is a point of inflection of a function f of x if f double prime at a is 0 or f prime of a is undefined. So finding the point of inflection does tell you where the returns are going to be diminishing. We're going to return to the worksheet and attempt at finishing off the first question. So we were in the middle of part D here. We finished up to part C. Determine the intervals on which f of x is concave upward and concave downward. So when you see the word concavity, it means you need f double prime. Well, we have f prime up here from part A. So f double prime of x, the derivative of 6x squared is 12x, plus the derivative of 6x is 6. And then what we're going to do is I want to know where this is positive and this is negative. Okay, that's what we have for concavity. So we need to see where the sign change happens. So I'm going to first set this to equal 0 and solve for x. So I get x to be equal to subtract a 6 and divide by 12. I get negative half. I'm going to put this on a number line. Now this process may seem very similar to what we did here, but that was for critical points and that was for increasing and decreasing. Okay, so you might want to do note cards to straighten all this out. Anyway, negative half is right here. I'm going to pick sample points from either side. 0 is good on this side, negative 1 here. We're going to substitute these. For concavity, we need f double prime at negative 1. Plug in negative 1 there, that's negative 12 plus 6, which is negative. So if you're a negative person, you frown. Concave down. F double prime at 0, 12 times 0 is 0, plus 6, positive, concave up. The way we leave our answer is we say f is concave upward, or we should go from left to right, concave down on the interval from negative infinity to negative half, and f is concave upward on the interval from negative half to infinity. Now at this stage, I want to go back to our notes. I want to add something to our point of inflection. The definition for the point of inflection is that it's a point of inflection if the second derivative is either 0 or f prime is undefined at the point x equals a, and an important part, the concavity of f switches on either side of a. Okay, so that's a key part. So going back to our example, over here, negative half is where the second derivative is 0, and on this side the concavity changes from being downward to upward. So to answer this question, determine all the points of inflection. We don't have to do any new work, we just borrow the point from here. It happens at x equals negative half, okay, because the concavity changed and f double prime was 0 there, but we actually need to write it as an ordered pair. So I need the y value there. Now to find the y value, we're going to do what we did earlier up here. To find the y value, we went to the original function. I need to find f at negative half. So it's 2 times negative half cubed plus 3 times negative half squared minus 12 times negative half. So one more time, I went all the way up here to the original function and I'm plugging in negative half. Again, feel free to use a calculator. I'm going to do it by hand. So that would be negative 1/8, 2 goes into 8 4 times, that's 3/4, and then that's 2 negatives, makes it a positive 6. Negative 1 plus 3 is 2/4, so it's 1/2 plus 6, which is 13/2. So that would be the inflection point. Okay. So there's one more part here where we put all of this together and come up with a rough graph. So that's the next page. I'm going to keep this sheet handy. It says here, use all the information obtained in parts A through E to graph f of x below. So negative 220 is an important point. Negative 220, I'm going to write maximum there. 1, negative 7, somewhere here, we have a min. And then finally, negative half, 6.5, positive 6.5, somewhere there is a point of inflection. To the left, the graph is increasing, so it's doing this, and it's concave down, up to the inflection point, and it's decreasing. It's decreasing from negative 2 to 1, decreasing from negative 2 to 1, then increasing, and it's concave up from here on. And again, you can type this into your calculators and verify this. It should work out. One final bit in section 4.2. This is a long section. Is a second derivative test. Now remember the first derivative test. Go back a page or two. The first derivative test told us how to find the max and min finding relative extrema using the first derivative test. The good news is the second derivative test also does the same thing. The second derivative test is used to find the relative max and min. So in order to be able to do that, how do we use the second derivative test? Well, the second derivative test uses the idea of concavity. Okay, so let's say f of x is given, and f of x be some function. To use the second derivative test, step 1, first thing is find all critical points. Now we need to go back a section for this. Critical points are from the first derivative, from f prime of x. Okay, and the next step, find f double prime of x. Let's see the critical points here. Let's call them C for critical point. Now if you plug in that C into the second derivative, if f double prime at C is positive, there's a relative something at x is equal to C. So let's pause here and try to fill up the blank here. If the second derivative is positive, the graph is curving upward. Positive person, they smile. The critical point then will give you your low point. This is your C value, which means you have a minimum there. So contrary to your intuition, positive means relative min, okay, because it's a second derivative. If f double prime at C is negative, if f double prime is negative, frowning, which means the critical point there is a max. So there's a relative maximum at x is equal to C. But if it's neither positive nor negative, if f double prime at C is 0, the test fails. Then you have to go back and use the first derivative test. The second derivative test is kind of handy sometimes. When we get to word problems, we'll show you how the second derivative test makes things a lot quicker. For now, the first derivative test might actually make more sense. Let's go back and do this example where we use a second derivative test to find the relative extrema for this function. So I'm going to first write this function differently. It's 2x plus, instead of 18 over x, I'm going to bring that up as 18x to the negative 1. So the second derivative test, the first step is to find all critical points from f prime, the first derivative. So then the minus comes down, minus 18, x to the negative 2. And as I said in the previous video, gotta first rewrite it. X to the negative 2 goes down here. I'm going to actually get a common denominator here. So we have, well, we don't really need to do that, I guess. There's another way to solve this. You can set this to equal 0. And then you can add this or send it over to the other side. So you get 2 equals 18 over x squared. Now you can multiply x squared to both sides. Cancels there. 2x squared equals 18. Divide by 2. X squared equals 9. And then take square roots. It's plus or minus the square root of 9, which is 3. So we have 2 critical points. According to the second derivative test, find the second derivative and plug in the critical points. And depending on the sign, you can make a conclusion. So back here, f double prime of x. The derivative of 2, 0. Here, bring down the negative 2, and you get 36x to the negative 3. Okay, that's a positive because we had 2 negatives. Write this as 36 over x cubed. Now you're going to plug in, one at a time, 3, and see what you get. It's 36 over 3 cubed, which I don't really care about the value of this. All I care about is that it's positive. If it's positive, then this critical point, 3, was a minimum. So we have a relative min at 3 comma blank. We'll fill in that blank in a second. Let's do the other critical point first. Negative 3. So it's 36 over negative 3 cubed. If you cube a negative number, it's negative. That's a positive. So you get a negative result, which means it's concave down there. Okay. So that's a relative max at negative 3 comma. To find the y value, this is something we've seen quite a bit recently. We go to the original function. So we need to find f at 3. F is up here. So it's 2 times 3 plus 18 over 3, which is 6 plus 6, which is 12. F at negative 3, 2 times negative 3 plus 18 over negative 3, it's negative 6 minus 6, negative 12. So there's your relative max. Try the homework, and if you have questions, send me emails. Read the textbook. There's plenty of examples, plenty more than I have done. So use the textbook and stay in touch.